So let's begin with Bayes' theorem. Recall that we had two different measures of accuracy: sensitivity, the ability to detect a positive state, and specificity, the ability to detect a negative state. And in the last video, I constructed a nerd test for my nerd party. This particular test, to make sure that only nerds arrived at my party, had a sensitivity of 80%. 8 out of 10 nerds got it correct, and a specificity of 90%. 9 out of 10 non-nerds got it incorrect. So how did I do? Is this a party that really is filled with nerds? Well, let's ask the question. Assuming the person did get in, how likely is it that that person is a nerd? Let's look at all the different people that passed the test. So I had 8 true positives, 8 nerds, and 1 false positive, 1 non-nerd. I'm going to do some basic division. 8 divided by 9 gives us about 89%. So if any person I walk up to in my party, there's an 89% chance they're a nerd. This is an application of Bayes' theorem. That vertical line, that part right there, is a conditional. The probability of A, assuming B happens, equals the probability of B, assuming A happens, times the chance of A, divided by the probability that B happens. And we can expand on this, all the different ways we can get B. This tilde means not A. So the probability that B happens, assuming A doesn't happen, times the probability that A doesn't happen. So let's apply this to our situation. What's the probability of a nerd, assuming the test comes back positive? Well, here it is translated: probability of a positive result, assuming they're not a nerd, times the probability of a nerd, etc., etc. Probability of positive result, assuming they're not a nerd. This right here is our chance of a true positive in this particular example. And this right here is our chance of a false positive. Again, this is just for this example. It would be completely different if I said, what's the likelihood of being a nerd assuming the test comes back negative? What's the chance of being not a nerd assuming the test comes back positive? It's different. But hopefully if you understand how this works, you can just move through the substitution and determine what's what. Now, keep in mind we have to figure out what's the probability of being a nerd. And in this particular example, I was assuming 50-50, right? We had 20 people, 10 nerds, 10 non-nerds. The probability of being a nerd is 50%, 0.5. And the probability of not being a nerd is 50%, 0.5. So let's do the same question, but use Bayes' theorem. We're going to make a table, a little tree. Probability of someone is a nerd, 50% chance. Not a nerd, 50% chance. If they are a nerd, the chance the test is correct is 80% because it's 80% sensitive. And there's a 20% chance it'll be wrong. If they're not a nerd, then the chance the test is correct is equal to its specificity, 90% of 0.9, and the chance that it's incorrect is just a 0.1, or 10%. This first one is a true positive. The test came back positive, it is correct. The second one is a false negative. The test came back negative, but that result is incorrect. I rejected someone who was a nerd. This one's our true negative, and this one's our false positive. So those true positives and false positives that we're going to be interested in this particular example, because we're wondering all the different ways to get a positive result. So to figure out of all of the tests I run, what portion of them will be true positive? And we can figure that out by just multiplying how likely is it that they're a nerd, or PN, times the chance that the test is correct, or this conditional right here, right? The chance to get a positive result assuming they're a nerd. And we get 40%. And we can do this for all of them. Just to multiply the conditional times the likelihood of the initial result, initial probability. So we'll have 10% of our total results will be false negative, 5% will be false positive, 45% will be true negative, etc., etc. And we can substitute this in. So now we have 0.4 for our true positives. So you have both on the numerator and the denominator. And we can put in 0.05 or 5% for our false positive. And when we get this, we get exactly what we got before, thankfully, about 89%. But what if 5% rather than 50% of people are nerds? Because let's face it, half the population are not nerdy. They're just not. They claim to be, but they're not. So it's the same scenario as before, except now I've changed this from a 0.5 to a 0.05 and from a 0.5 to a 0.95. Everything else is the same. And here's the new result. Note, now we can substitute it in for our results. So we'll go to 0.04 here, and 0.095 there, and we get a measly 29.6% chance. If I walk up to anyone in my party, there's a less than 30% chance that they will actually be a nerd. Even though I had a nerd test, even though that test seemed pretty accurate. But because being a nerd now is so rare that my false positives will overwhelm my true positives. This is one of the key insights of Bayes' theorem. One of the most interesting results. Even if a test is seemingly accurate, if it's testing for something that's rare, the results won't be as good as one might initially think. It doesn't tell you as much as the intuition might suggest. Thanks for watching.